Thank you for the kind introduction, and thank you all for coming to this late session. My name is Kirchner, and I'm presenting joint work with my colleagues Jonas Möller, Marius Musch, David Klein, Konrad Rieck, and Martin Jones. So our paper is called Dancer in the Dark, Synthesizing and Evaluating Polyglots for Blind Cross-site Scripting. So really just a brief introduction, as I'm sure the people that came to this session are familiar with cross-site scripting, but for the rest, it's a consistently featured top 10 webhacking technique where insecure use of input from HTTP requests can lead to script injection. So using inputs is fine, as long as everybody behaves, but always keep in mind that your users can also be attackers, so we have to test for cross-site scripting. And state of the art of cross-site scripting detection still revolves around finding where input from HTTP reaches HTML. If you have code available, you can do code reviews, right? But most likely you will just send requests and inspect the responses. This can also be automated, for example, via taint analysis, where inputs are followed from source to sink. However, that does not really work for blind cross-site scripting, and I'm going to show you why. So we have our attacker as usual, and they are sending malicious inputs to a website. From there on, these inputs travel to a web server. So far, so good. But now, these inputs find their way into some backend. And since nowadays most things are web-based, our operator, which is the victim here, might use web-based tools too. And if these tools are vulnerable just in the same way as front-end back applications are, then our attacker has won and there's code execution in the backend, which is severe. So let's test for blind cross-site scripting. We have our researcher, and they can inspect the front end just as usual, right? And they might have a general idea of a backend, but there's no feedback channel, so they cannot inspect the responses the operator gets from these tools, which is a problem because now our bread and butter of cross-site scripting detection does not work anymore, as we have no feedback, so we are essentially blind. So then, how do we deal with this? Maybe let's do some blind testing. The problem with blind testing is that we cannot know in which context we are in. So there are different contexts, and I've brought you 3 here. The first one is in the HTML parser. So you need an exploit that works here, like you close the anchor tag, inject your script, and so on. So the second one is in the URI parser, where you can use JavaScript URIs, for example. And these are a very specific case. And in the third case, you are directly in the JavaScript parser, so you need another different exploit. Great, so we have unknown contexts, and we don't know where we land. So our idea is to find a solution that works in all contexts, which brings us in the direction of cross-site scripting polyglots. And polyglot means that you are able to speak several languages, which translates to our cross-site scripting polyglots, as they are designed to work in many contexts, which is made possible by the interplay of different parsers which are involved in serving web applications to us. So cross-site scripting polyglots are already applied in the industry, for example by Google, as a time saver for web testing. How do they help us? Recall the slide from previously where we have 3 different contexts and substantially different payloads, but we can simplify that by using just one simple polyglot that covers all these 3 injection contexts. However, please, disclaimer, this is a very simplified polyglot. Real-world vulnerabilities require much more complex payloads, right? So still, we have an idea, we have a way to work in unknown contexts. Let's tackle the next problem. We have no feedback, yeah? We are in some backend, but polyglots are essentially a way to transmit a payload. And here our payload is an alert, which is not of much use in this backend. So instead we use something like an import statement. And I'll show you how that works. So we have a polyglot, and it ended up in some backend. And that backend is vulnerable to blind cross-site scripting. So the polyglot will execute, and its purpose is to load a feedback script from the monitoring server here. So since imports send HTTP requests, this is our first piece of information we get. Now, of course, the monitor happily replies with the feedback script, and its purpose is to collect some minimal information from the backend. So you can load some additional code, and that code collects the title and parts of the URL of that backend. This information is returned to the monitor, which is the second packet of information you get. And in there, you, of course, get the IP address and a user agent if it is attached. Great. So also see that there's an identifier being passed around here, which is used for tracing a submission of a polyglot to essentially the feedback you get. Great, now we have a feedback channel, and we can now focus on creating one polyglot to rule them all. However, we can't, as at least some contexts are syntactically incompatible, so they are partially mutually exclusive. Okay, so we end up with a different form of optimization problem, where we focus on creating a set of complementing polyglots that together can solve all the injection contexts. And towards this goal, we have three components. First, we have a cross-site scripting testbed. Yeah, we need a testbed of all the injection contexts we want to cover. Second, we need some form of polyglot synthesis, which puts out some polyglots, and you can see if these solve the testbed. And then you can apply just simple set minimization to find a minimal set of polyglots that solves this testbed. The first two are the most interesting ones, so let's look into them in more detail. For our testbed, we resort to Google's firing range, which is a state-of-the-art cross-site scripting testbed, and it is internally used to evaluate how detection tools work, how good they are. So we consider a subset of Google firing range tests consisting of 111 tests, which are related to cross-site scripting. We excluded out-of-scope contexts like SVG, AngularJS, and Flash because they have substantially different syntax. And we only consider tests which are still solvable, which we determine in cooperation with Google. So for our generation, we actually borrow an algorithm from game theory called Monte Carlo tree search. So it's a heuristic search algorithm, which essentially simulates games to determine the next best move. Details on that are in the paper, so yeah, please look into that. All right, essentially we are playing a lot of rounds. We synthesize polyglots, and in follow-up generations, we synthesize polyglots that focus on yet unsolved tests. And we ended up with about 4,000 polyglots to choose from after 2 months of generation on and off. So then it's quite easy. You can just apply some simple set minimization algorithms, and we end up with 7 polyglots to rule them all. So let's look at the graph for a bit. On the y-axis, you have our 7 polyglots, and on the x-axis, you have the 111 test cases. So whenever a polyglot is able to exploit the test case, there's a square, and special emphasis on the blue diamond, which indicates that this polyglot is the only in the set that can solve this specific test. So, of course, each polyglot needs to have at least 1 diamond, otherwise it makes no sense for it to be in the minimal set, right? Okay, so at this point in our work, we have learned that we can create polyglots that solve this synthetic Google firing range testbed. But the question still remains if these also work for real-world vulnerabilities. And the easiest way to obtain real-world vulnerabilities is through client-side cross-site scripting, so which is what we do. We conduct a small crawl on top 10K websites using Foxhound, which is a state-of-the-art taint engine, and taint-based exploit generation from related work. Then we try to exploit vulnerable flows using taint-based exploit generation, as well as our polyglot set. So our hope is that we are at least competitive with these perfect knowledge taint-based exploits. And surprisingly, we are, absolutely. We even solved 2 more tests in these vulnerable flows. So with tests, I mean vulnerable flows, of course. Yeah, there's a huge overlap. There are also some cases which are only solved by one of the 2 approaches. Details on that are also in the paper if you're interested. Great. So we have learned it works for real vulnerabilities on the client side. But getting back to the actual topic, blind cross-site scripting, we need to conduct a second experiment. So what we do is we conduct a shallow crawl of Tranquil's top 100 K-domains. Shallow means we basically just visit the homepage and some same-site links up to a depth of 5. We are completely vanilla, so it's an unauthenticated request. We are defensive. We conduct preemptive canary tests to look for reflections, which we then skip. And essentially, the polyglots are only included in simple HTTP requests. So for GET requests in headers and parts of the URL, and POST requests to forms which have been previously tested. So if a backend is then vulnerable to blind cross-site scripting, we receive feedback. Great. So this is what we did for about 20 days, and we ended up with 18 vulnerable backends with this very trivial crawl. So these backends were triggered by simple HTTP requests that contain polyglots, right? It's a bit crazy. So we have seen custom tools, but also popular software, and among them 2 major platforms for logging, monitoring, reporting, it's the name they give themselves, and industrial detection and response. We disclose the findings and this was well received. So from the technical side, we have seen that each polyglot was able to trigger backends. And additionally, most polyglots were the only polyglots to trigger certain backends, which validates our approach of having this set of polyglots. So to summarize, we've learned about the blind cross-site scripting scenario, and we've learned about our 7 polyglots, which we generated using Monte Carlo tree search to cover parts of the Google firing range which are accessed as relevant. Then we applied these polyglots, and we've seen that they work for client-side cross-site scripting and also in the blind cross-site scripting scenario. That concludes my talk. Thank you, and I'm happy to answer some questions.